So what's going on, guys? So for the last presentation, we actually finished our feed-forward propagation of our model, and we fed it our inputs of arguments 2 by 4, 2 features, 4 training examples, and we returned our 1 by 4 vector corresponding to the guesses, right? And these guesses are just based off of the random weights and biases that we initialized using tf.randomNormal and tf.zeros, okay? So with that, we want to have a good idea on how bad this guess is, right? So we're going to delete that, and we're going to work on our loss function. So for our loss function, so we have build here, we have call, so we're going to implement that right underneath here, okay? And we're going to call that del self.compute loss, okay? So it's going to be another class method, and as of right now, we'll have it doing nothing, okay? So what exactly do we want to do? Okay, so we want to, well, what we want to do is we want to take this example, subtract it from our label 1, square it, and take the average. So that's the mean squared loss error. So that's what we want to do. So under compute loss, what we can do is, okay, so we know we're going to return something. And what we know we want to do is, okay, take all these and return it, okay? So our loss at some point will have our predictions and the true y's, okay? So we'll call that y predict and y true. So what we want to do is we want to use all TensorFlow math ops, just because when you're working with TensorFlow math ops, it's acting on the tensors itself. You could implement everything as NumPy functions and turn them into tensor functions, but it's just much easier just to use TensorFlow math ops. Okay, so what we know is what we're going to do is, okay, so it's always good to just have the bare bones. Okay, so we want to do y predict minus y true, right? And we know we want to square it, and we know we want to divide it by the number of training examples, right? So we know that's pretty much what we want to do. So this subtraction, we can do tf.subtract, y predict, y true, and actually you can do this in TensorFlow and it still works because of eager execution, but I just like to do it, you know, actually that just makes things easier for us, okay? So what we're going to do is we're going to take y predict, subtract y true, so take this, subtract 1. Take this, subtract 0. So we're gonna do that. And then what we're going to do is we're going to square it for the mean squared error loss. We're going to sum it using tf.reduceSum, and then we're going to divide it by 4. Okay, so that's good. So that's just squaring it and divided by 4, and then we're returning the loss and compute loss. So what we can do is we can just make sure that works. So what we're going to do is we're just going to print. So because this is a class method, we can just call it with model.computeLoss out here. And then what we're going to do is we have to pass in our y predict. So our y predict is here, right? So we can actually just remove that, pass it in here, and we know our y true is y, okay? So we actually just sort of combine those steps. And then print, and we see that it did in fact take one of our guesses, subtract the true value, square it, divide by 4, and sum it across, right, for our total loss, okay? So this is sort of where we can get, we can actually start maybe implementing this function right here to determine the accuracy, just to see exactly what it looks like, okay? So we know that, I had to explain that what we want to do is we want to print out accuracy and loss every single iteration, right? So how exactly do we want to do that? Just look at the time. We seem to be good for time. So we want to print some sort of statement. We're going to call it epoch. So epoch is going to be the current epoch. So we're going to call it epoch. We're going to print it to 4 decimal places, if that's the right notation. So at epoch this, what we're going to do is we're going to do the loss. And what is the loss? So the loss is whatever this is, okay? So rather than print it, we're just going to call it ls. Remove that. And then later on, we're going to print out accuracy, but for the time being, we don't have accuracy implemented yet. So let's run this. Invalid syntax. I actually, for the love of me, cannot remember the notation. Yeah, okay, that's embarrassing. Okay. Yeah, so just the other way around. Decimal places to 4, run that. And we can see at each of these epochs, the loss is the same because we're just, pretty much all we're doing is the computing the loss and the forward propagation every single iteration, and we're not changing the weights and biases. So of course the loss is going to stay the same. And for this, we just want to maybe print to 3 decimal places. So that's neat. We'll make it 4. Okay. Looks good. Okay, so we got that. So what we really care about now is training our model, okay? Because that's all fine and dandy, but this is a model that's not really doing anything. It's just forward propagating and isn't telling us really anything about what the model is trying to do. So we can sort of implement that over here. So we want to evaluate our gradients. So how do we want to do that? So in TensorFlow 2.0, with eager execution enabled, we don't have to worry about TF dots, those terrible TF.session sessions. We can just go TF.gradient tape as T. What we do is we want to pass in our loss function here. The reason why we want to do that is because what happens is when you pass it under this, I think this works as a decorator. I might be wrong about that. But what that is it's actually computing the TensorFlow graph so that when it does the back propagation, the TensorFlow graph is already built, and then it just jumps from node to node, right? Okay, so that's good. So actually we want to calculate our gradients here. And how we want to do that is we want to produce our gradients. And we want to, so this is why I was saying how you didn't actually need to know how gradient tape works in order to initiate gradients. The reason why is because when we compute or we create that TensorFlow graph, because all the nodes are already set for us, it's very easy to determine gradients. All you need to do is pass in our loss that we have and pass in the variables we want to be trained, okay? As you can see, all of our variables here are called different things, self.layer1, b2, right? So they're all in here. So we could actually pass them all here, but it might be actually easier to just, okay, so we have them built there. We can actually call them over here self.variables, okay? So I think in TensorFlow layers, they call this trainable variables, I believe. I think that's what they are. So if you wanted to grab those, that's what you'd have to call them. So we have layer 1, layer 2, layer 3. So you can see that over there. And then we have our 3 biases, okay? Which, as you can see, I named incorrectly, right? So I just actually, oh no, that's right. Okay, layer 1, 1, 2, 2, 3, 3. Okay, just checking. So we want to grab all our biases. 1, 2, 3. So we'll just expand this for now, and then we'll take a better look. 1, 2, 1, 2, 3, 1, 2, 3. Okay, and then that should wrap if I do that, okay? So we know all our variables are called self.variables, and we still look at each one over here when we pass it through the feed forward, but over here, what we actually want to do is call or retrieve our class variable self.variables, but outside of the instance, that's called, we can get it by using model and dot notation, variables like that. Okay, so the question is, what exactly is going on here? So with TF gradient tape, we computed the loss. What this is doing is it's saying, okay, determine all the gradients of these variables, the list of these variables, with respect to the loss, and produce the gradients, okay? So rather than computing this, actually over here, what we can do is actually, you know what, let's just look at the gradients. Let's pretend it's with tf.gradient function, st, pass it in. Grades, okay, so it didn't like something, unsupported format string to list format, okay? So let's not do that. Let's just say for the first epoch, let's see exactly what these gradients look like. Let's just make sure they make sense to what we expect, okay? So there's a lot of numbers here, so let's make things easier. Say we have a 2x4 architecture, right? Just so everything can be seen in one. Integer division by 0, we don't need to worry about that just because this has to do with the fact when you have one training epoch. Okay, so what exactly were we looking at here? Well, we know self-taught variables is 6 long, 3 weights and 3 biases. So when you compute gradients, it'll actually compute the gradients in that order. 1, 2, 3, 1, 2, 3. So what we'd expect is that our first layer for our weights will be a 2x2 corresponding to 2 features, 2 input neurons. The second will be 4x2 corresponding to the first layer going into the second layer, makes sense. And then the last one, the output is 4, so it should be 4x1 because we're feeding 4 of the second dimension into the final neuron, which gives our guess as which is the final sigmoid. And then our biases are very similar, where we only have, let's just make sure. Okay, so we have our biases as 2x1, 4x1, and 1, right? So 2x1, 4x1, and 1, right? So those biases are just feeding into the incoming layer, right? So these all make sense to us, even if these gradients don't really mean too much for us right now. What we know is that our model is learning something, and that's what's important. So this might not be a good idea, but let's just take a look at what the gradients are doing. Okay, that didn't work very well. Okay, so what we're going to do in the next tutorial is we've implemented our gradients, we've calculated them. The next thing we want to do is actually apply the gradients, right? So those are our partial differentials, and we want to apply the gradients on every single one of our model variables, which is as easy as taking these model variables and subtracting the gradients and multiplying our learning rate. And we'll do that in our next tutorial, and we'll see you guys next time.